We're talking about Unit 1, Entry 7, Physical and Chemical Properties and Changes. So this is just a refresher from a couple of weeks ago at least, that all matter, all stuff is made up of different things, right? We have pure substances and mixtures. On the pure substances, we can have elements or compounds. On the mixture side, we could have evenly mixed things, solutions, usually things that dissolve in other things. And then we have colloids and suspensions. Oh, and my bad down here. This should be a heterogeneous mixture that settles out over time. But in general, you have all matter is composed of stuff. And then we also looked at how all matter is in a specific state of matter. You have solids, liquids, gases, and plasmas. And depending on which state of matter you're in, you have different amounts of energy. Okay, so realize this way, as I add heat, which is energy, I go from solid, liquid, gas, and plasma. And like this phase change going from solid to liquid or melting, we would know that. Or liquid to gas, evaporation, we would know that. Most of you are able to say those things. And then maybe this one is new. We did ionization and so forth. But we can also go the opposite direction. So these things are called phase changes. And that relates to all of our matter that we have. And that's where we start today. So phase changes. This is when a substance undergoes a phase change or changes their state of matter. Again, pause here if you need to. In order for that to happen, we either have to absorb energy or release energy. And absorbing is endo. Note it has an N like in, and exo like out is the release of energy. Now, oftentimes endothermic particles feel cold, or reactions feel cold to the touch because it's absorbing energy from your hand, and exothermic feel hot because energy is going into your hand. So those are often common phase changes. Again, pause here if you need, otherwise I'm going to move on. So realize that every element or compound has different properties, and these two properties fall into different categories. That was out of order, my fault. So phase changes, we have all of our different phase changes here: evaporation, freezing, melting, condensation, and the two new ones for us probably are sublimation and deposition. This is solid to gas and gas to solid. This is on your document. And then you have this table where it has a letter and an arrow. So like liquid to solid, that would be freezing. So that'd be like letter Y. And you're asked to fill out this table. So let's do a couple together. So let's find letter T. So I'm going from gas to solid. Gas to solid is deposition. So I'm not going to write everything out just for sake of time, but deposition is here. Now, in order to go from a gas to solid, do my particles have to gain or give off energy? And they have to give energy. And the reason I know that is because my particles are moving slower at the end. Solids move less than gases. So when it gives off energy, that is considered an exothermic phase change. We'll do another one together. U, solid to liquid. Solid to liquid right here is melting. Probably another one that you know. I'm just going to put an M there. That is a gain of energy. And how do I know it's a gain of energy? Because as a liquid, my particles are moving more. That would be endothermic. Okay. So why don't you try to fill in the rest of the table here? I'm going to pause the video and write in the answers, then we'll talk about them in a second, but see if you can identify them. Quick, trying it. Letter W right here, gas to liquid is condensation. Letter X here, where are we at? From liquid to gas is evaporation. Y is liquid to solid, that is freezing. And then last one, letter Z, I have solid to gas, that's sublimation. And that's my last phase change. So anytime I give up energy, it's exothermic. So every give is exo, every gain is endo, and it's all about particle motion. Do my particles move slower or slower or faster at the end? And notice every time I went up, I had to increase my motion. So like letter Z, I had to increase my motion, so I had to gain energy. That's endothermic. So let's connect that back to properties. So phase changes are considered physical changes because the identity of the substance stays the same. Imagine you melt an ice cube, it's both water on both sides. And state of matter, like solid, liquid, gas, or plasma, is considered a physical property because it does not describe how a substance reacts. So what are physical properties? Physical properties describe the characteristics of a substance, not how it reacts. Example would be boiling point, texture, color, or state of matter. These are other physical properties over here: melting point, density, volume, weight, if it's magnetic, state of matter, texture, luster, solubility, and so forth. These are the things that describe how a substance is, not what it will do under certain situations. Now, chemical changes describe how a substance's chemical composition or its identity will change under a specific set of conditions. Example would be flammable, toxic, corrosive, that type of thing. So like an Alka-Seltzer tablet, it produces gas, right? And here it is combusting. You see the fire released as energy, and those are evidences of chemical changes happening. So you'd say that wood is combustible. You'll describe what it will do in the presence of heat. It will combust. Lead is toxic because you're describing what it will do to our human cells. It will kill them. So physical and chemical changes, each substance has its own set of properties, and when the conditions change, these properties may or may not change. Okay, so if I were to add heat to an ice cube, it would melt. If I add heat to a log, it will burn. So when the identity and the properties change, that's a chemical change that's occurring. When the properties do not change, it's physical change. So it's all about, is the substance the same thing? And that's really all the question that you'll be asking as you go through this. So we're talking about physical and chemical changes. The main idea here is all about identity. Does the identity change? Yes, chemical. No, physical. You might be asking, well, Mr. Peters, how do I know? Well, notice the physical change, it's still a log. Even if I cut it, the log's a different size, but it's still a log. When it's a chemical change, the log is not the same anymore. It turns black, it gives off heat. Those are all evidence of chemical change. And there are 4 evidence of chemical change that you'll have to know, and these are important. That when gas or bubbles form, like the Alka-Seltzer, if I go back, that would be a evidence of chemical change. When a solid forms, or when the color changes, so from brown to black, or energy change, when I see light, when it gives off sound, or temperature change, those are all evidences of chemical change. So regardless of the type of change, energy is always involved. And we have 2 ways to describe that energy change, endo and exothermic. But the idea here is that the total amount of energy cannot be created or destroyed. So total energy is conserved. And that's called the law of conservation of energy. So the total energy always remains constant. And if you were to go into advanced chemistry, that idea becomes very, very, very important. So in our chemical reactions, the speeds of the reactions are impacted by a couple different things: temp, surface area, mixture, pressure, particle size, catalyst, and concentration. So let's talk about those. So think about this. If I had a sugar cube and I dropped it into, sugar cube, something that looks like this, nice little drawing here, boop, 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 versus granulated sugar, which of those is going to dissolve faster if you put it into water or into coffee? The granulated sugar. Why? Because it has more surface area. What if I stirred it? Would it impact how fast it dissolves? Yes. Stirring is going to increase how fast it dissolves. What about if I increase the pressure? On this example, it would have no impact, but if I were to increase the pressure, let's say of gasoline and oxygen in a car engine, then it's going to combust much faster. If I add hot water, that's going to combust or dissolve faster as well, because there's more collisions. So this is in your table, and you don't have to write it down, but I just want you to listen through before we get to the homework. So when we're talking about concentration, we're talking about the amount of stuff. So if I have more stuff, reactions are going to happen faster. If I have less stuff, slower reactions. Surface area means more particles are exposed. Think about if you had to, trying to think of a good example here. So go back to this example. The only sugar that can get dissolved is the one on the outside in the cube. But when they're all exposed or my surface area is higher, the reaction will happen faster, even though dissolving is not a reaction. Temperature, the particles are moving faster, so at higher temps, they're more likely to react. Particle size, when they're bigger, they're more likely to run into each other, which means they're going to react more. Pressure, which only impacts gases. We saw this with behavior of gases. When there's more pressure, the things are going to be closer together, and they're going to be moving faster, so the reaction will happen faster. And if I add a catalyst like in a cell, or I mix or stir something, the reaction will always increase the rate of reaction. So let's think about this. Let's think about this reaction and then break it down here. In the beaker below, barium hydroxide and ammonium nitrate, two compounds, are reacting to form a new product. This product releases heat, which means it's going to be warm to the touch. It's going to be warm. Okay, so is that endo or exothermic? It's exo because I can feel the heat. Evidence of chemical change, you could say temperature change, which is energy, or color change. What could speed up the reaction? You could warm these up, you could stir it, any of that type of thing. What could slow it down, cool it down, add higher concentrations or more particles, things of that nature. So we're going to roll through the beginning part here, and then I'll have you complete the homework. So this first part, you're going to label each of these as endo or exothermic. Remember, if I go from less energy to more, like sublimation, that's endo. And if I go from gas to solid, I have to release energy, that's exo. So label each of these as endo or exothermic, and then list them over here in these two questions. Okay. Next part, what you're going to do, you're going to say, does this speed up, slow down, or have no effect on the reaction? So 1, 2, or 3, and then list the factor that's being changed. So putting leftover food in the freezer so it doesn't spoil, that is going to slow down the reaction. The thing that's being changed is temp. Let's do one more. Piston with car engine compressing fuel, that will, 1, speed up the reaction. What's changing is the pressure of the gases. Okay, so look at these other 3. What are the factors being changed, and what is it going to do? It may be known, maybe none. 6 through 10, what evidence of chemical change do I see? These are my 4 evidences listed here. Gas for solid, color change, energy change. So if I look at these, I got mixing 2 wet liquids to produce a brown solid. You could put 2 here, color change, or I would say solid forms. It's probably the best one, solid formation. Okay, so you're going to use the other ones each once, or maybe not at all. Chemical, physical, neither or both. Condensation is a phase change, so that's a physical change number 2. Burning of a candle has melting, which is a phase change, which is physical, but it also has the combustion, which is a chemical change. So that's actually 1 and 2. So it's going to be both. See how I got you there with the 1? That's number 4. So you got chemical or physical, neither or both for these. Okay, that's it for this one. Don't submit your notes yet. Wait till you take notes on Thursday for acid and base stuff as well. All right, love you guys. Talk to you later. Bye.